All right, so here are a few similar harmonic motion MCQ practice for you to follow. The first one's this one. You have some mass on an ideal spring. It has an amplitude of 50 millimeters, and then it has a time period of 2 seconds. And it wants you to find the maximum speed during this oscillation. So hopefully by now you understand that when the spring is stretched to the right or compressed to the left, once you let it go, all of that potential energy stored in the spring will be converted to Ke, and that happens at equilibrium where x equals to 0. Okay, so let's go ahead and crack this out. One, I noticed that the amplitude here is given in 50 millimeters, so make sure you pay attention to units as you practice these problems. 50 millimeter needs to be converted to meters only because all the answers are in meters per second. So to convert 50 millimeters, you just take the starting value and you would just multiply by the conversion factor. For every 1 meter, there's 1,000 millimeters, so make sure you put these values in the right place. Millimeters cancel out, and that leaves you with just 0.05 meters, okay? Well, to find V max, I think the easiest way to do it is just use this particular function where it's just the amplitude times the angular frequency. Other than that, you already know A, because A is 0.05 meters. You don't know what omega is though. However, I think this problem we really assess to see if you understand the relationship between omega and time period. Omega can be broken into 2 pi rad divided by capital T. 2 pi rad is 1 complete cycle. And then capital T here is the time for an oscillation to go there and back. That's capital T. Well, capital T is given to us as 2 seconds. So I'm just going to plug and check here. A is 0.05 meters from the converted value. And then 2 pi rad divided by 2 seconds. 2 seconds given in the problem. The 2 on top and bottom cancels out. So really, all you're left with is just 0.05 times pi. And if you do that correctly on your calculator, you'll get 0.157 meters per second. And that is closest to answer B. Now, the other way to do it, again, it all depends on how familiar you are with these harmonics functions. V at any point during the oscillation can be calculated using this particular function, omega times the radical of the whole quantity, a squared minus x squared. So I made a note for you here. I would not use this way, but in case you don't, you know this function, you can apply it. And if you apply it correctly, you'll be fine. Max speed occurs at the equilibrium. So here, because the V that you're trying to find is V max, well, in this particular function, well, V would now have a subscript V max. But if you use this, then you would just set x equal to 0 because the question wants you to find V max, and V max occurs when x equal to 0. So really, if you plug in that particular true statement, x equal to 0, well, a squared minus 0 is just a squared on the bottom here, and that will leave you with just really the same expression. On this side, V hasn't changed, omega is the same, and then square root of a squared is just simply a. So as you can see, it kind of loops back to my original strategy here. If you know V max is just a omega, just crack it out because the information gives you time out already. Okay, but if you do it this way, then you just have to understand where Ke is max, which is equal to where x is equal to 0. Okay, all right, let's move on to the next one. For this one, the amplitude of an oscillation is given. And it has some time t and it has some energy E, and it wants you to figure out which statement is true when the amplitude is double, right? Okay, so it says here what would happen to t, the period of oscillation, and E, the energy of the system when A is double. So here your only answer choices A, B, C, D, and E. I think this one's pretty light work if you know your harmonics function. Once again, the oscillation period for a mass spring system here is just 2 pi radical m over k, where m is the mass of the block and then k is your spring constant. And then, so as you can see here, period does not depend on the amplitude. It depends on 2 quantities, the mass of the box and then the spring constant. Okay, so now the other variable that I want you to compare is E, the system. Well, here the energy stored in the spring is due to potential energy. So I'm just going to say that E max is the same thing as PE max, and PE max is 1/2 K A squared, where instead of X you would just replace X with A because this is the maximum energy stored in the spring. Okay, and I highlight the square because A is squared. All right, so all you have to do if you know these functions, you just have to make a quick assessment. Here it says T depends on M and K. I don't see an amplitude in this expression anywhere. So therefore, I'm just going to cross answers out. That doesn't make any sense because A is independent of the amplitude. It doesn't change. So I'm going to cross out choice A. Or actually, well, before I cross out choice A, here I wrote on the right side, E depends on the amplitude because, again, if you just read the expression, it's 1/2 k a squared. So of course, since a is in there, it depends on it. All right, so let's go ahead and use deduction here. I'm just gonna cross out a because it says both t doubles. Well, first of all, I don't even care about e. The fact that it says t doubles is wrong because t stays the same because it does not depend on amplitude. So see B says t is reduced. Well, no, it can't reduce. It stays the same. So I'm gonna cross that answer choice out. And then C says t remains the same. So I'm gonna keep it as is. D says t remains the same. So I'll keep it as is. And then E says t is double. Well, it cannot change. So it can double, it can halve, it just can't change. So that leaves me with choice C and D. Okay, so I know that t has to remain the same. So I'm going to read the second half of the statement. Choice C says t remains the same and E doubles. Well, if you understand that 1/2 k a squared, well, a is square. I highlighted the exponent for you there. Well, if you double a, doubling a would actually cost this particular e to be quadruple because 2 square will give you 4, right? So it's not just the a that's being square. It's like the whole new quantity is being square. So the new value is 2a. So you have to square the 2, which is 4, and then the a squared remains. So really, there's a coefficient of 4 in this particular word. So I'm going to cross out C because this is not a linear function. It depends on a squared. Doubling a quadruples your energy. All right, so just by deduction there, I'm just going to go ahead and choose D as my answer. Okay, let's go ahead and move on to the next one. So for this one, I think this one's a little trickier. Here you have a simple pendulum with length L, it has some mass M, and then it has some amplitude A. So it wants you to find the maximum tension in the string. So as this object oscillates back and forth, so I provided a little animation here for you to follow. So this is a simple pendulum where it goes back and forth, and then keep in mind that A is not constant because A depends on theta and theta changes. Okay, but the one thing I do want to point out here is if you look at V, V is max, it's biggest at the equilibrium. So the blue arrow is longest when the bob here, or I'll just call it the bob, or the mass here, just returns back to the vertical position, which is at the equilibrium. All right, so let's go ahead and do it. Well, to do this one, you have to identify a couple of concepts here. At the very bottom of the swing, there's tension in the string, and that's going to be pointing up towards the thing that's holding it, in this case the ceiling. And then at the same time, there's an F of G pointing against it. However, because this particular mass is constantly moving, left and right, or oscillating back and forth, the tension and F of G cannot be equal, right? This is not a stationary problem. This is not a static problem. The fact that this is oscillating left and right suggests that at the bottom, T has to be greater, okay? So you notice I drew my vectors here. T is greater, is pointing upward, and then F of G is pointing down the page. So here, I'm just going to go ahead and say that net force at the lowest point, which is your centripetal force. So centripetal force here is just tension minus F of G. I subtract these two quantities because they're pointing in opposite direction. So the net force is really your centripetal force here. So here, I'm just going to break up F of C into mv squared over r. And then on the right side, I haven't done anything. But keep in mind, the question wants you to find maximum tension, and maximum tension occurs at the very, very bottom of the swing, which is at the equilibrium. So if you've done all your centripetal force unit stuff, hopefully this is just a recap of that particular concept. So I'm just going to go ahead and solve for T. To get T by itself, I'm going to move the negative F of G to the left side. So I'm just going to add it to the left side just to isolate for T. As you can see here, you have, known quantities, right? You know what M is, you know what R is. R is just the length of string because that's the radius of, quote unquote, the circle. And then F of G can be broken out into mg's, which I'm just going to go ahead and do so. Okay. However, at the same time, V, if you kept up with the previous example, V max is A omega. So I just replace V max here with A omega. Okay. Again, V max occurs at the equilibrium, and V max is just simply A, the amplitude of the oscillation, times omega. And then there's the square outside, so make sure you use parentheses when you substitute. So here I'm just going to distribute the exponent to the A and the omega. See, here I highlight omega squared for you because you notice all the answers here don't have an omega in it, right? So if you look at all A, B, C, D, and E, I don't see an omega. So that's kind of a ding, ding, ding that you need to get rid of omega so that you can get into the format that the answer is presented to you. So here, if you know, you know. If you don't, hopefully review your summer harmonics notes. The angular frequency for a simple pendulum is just the square root of g over L, where g is or acceleration due to gravity on any particular planet, and then L is just the length of string. But this is omega. I need omega square. So I'm going to take this and I'm going to square it. So I want to turn omega into omega squared by squaring both sides. Yeah, squaring both sides gets rid of the radical. So really omega squared is just g over L. And from here really is just recognizing what you can and cannot do. You have an ma squared times g divided by L, and then you also have another L on the bottom. So you can just combine those two L's on the bottom. That'll give you L squared, because L times L is L squared. And here, as you can see, you have an M and a G and then an M and a G. So really you have two terms with MG as common terms. So I can just go ahead and factor that out. I'm going to factor out MG because both these terms have an MG. So if you factor out MG on this term that I'm circling back and forth, those stuff that's left over is A squared over L squared, which is right here. And then if you factor out MG, this just turns into a 1, and that's where the 1 is. So at this point, if you just look at all your answer choices, there are 3 answers that has the plus 1 in it, and then the only answer choice that has an A squared over L squared is choice A. So that is that particular answer there. Okay. All right, let's move on to the next one. So for this one, it says a particle of mass 0.1 kilogram. It's oscillating and has an amplitude of 0.1 meters. And it says that when it passes the mean position, its kinetic energy is 8 times 10 to the negative 3 joules. What that means is essentially when it passes the equilibrium position, that it has a KE. So this KE is KE max because it's at the mean position. And it wants us to find the equation for the motion, given that the initial phase of oscillation is 45 degrees. So this is just fancy for saying it doesn't have to start at 0 all the time. Okay. So let's go ahead and do this. I think for you to really pick out an answer for this one, you just have to be able to visualize this particular shape. Here's the circle. Again, something in simple harmonic motion can be visualized as something just going around a circle back, continuously. So here, I'm just going to draw my x and y coordinate. This is my amplitude. The radius is now just called the amplitude because from 0 all the way to the edge is called the amplitude. So the object is bound between far right and far left, which is the radius. But instead of calling it radius, the simple harmonic unit just calls it amplitude. So this is A as well. So all the radius is just now capital A. But here, this is theta, because I'm just going to use referencing touching the x-axis here. And then this is the x-axis, and then this is my y component here. I don't really care about the x right now because the question is all on y. But if you think about it, if you break this amplitude into just a right triangle, the dashed red line, that is your y position. Okay. And then if you want to, you can also draw another dashed red line that represents your x. Again, just make a right triangle. All right, so y here is your sine because it's opposite of this particular angle. So right away, I can go ahead and just write this out. Y is equal to A sine omega plus the phase shift. So this second term is just your phase shift. Once again, things don't always have to start at 0. Like in linear kinematics, the initial position of an object doesn't have to equal to 0. It can be a negative value, it can be a positive value. If it is, you just add it to the system. If it's 0, you just leave it out. All right. So here, I'm just going to go ahead and break up theta into omega t. And then from here, I can just kind of really pick an answer that matches, one of these particular statement. Okay. A is given as 0.1 sine omega t. And then the phase shift here is pi over 4. It's pi over 4 because 45 degrees. If you know your unit circle, I just pull it up here to remind you. Here's pi over 4, and pi over 4 corresponds to 45 degrees. So you need to be able to convert 45 degrees into radians. So if you want to do that, you can just convert 45 degrees times for every pi, there's 180 degrees, and you'll get pi over 4. Okay, or you just know your unit circle and just use it. All right, so that's where the pi over 4 comes from in my work. So you don't want to put 45 degrees here because omega is in rads. So you want to make sure you convert degrees into rads. Otherwise, you can't take sine of stuff with different rads and degrees all in the same together. All right, I'm going to cross out A here because just right away, based off my work, it's a sine function, it's not a cosine function. So I'm also going to cross out D because that says cosine. And then E is just y. It says cosine, but it also says the amplitude is 0.2, which is not. The amplitude is 0.1. Okay, so really here, right off the bat, I can cross out 3 answer choices. And I'm going to leave B and C for now because both of these have the right amplitude in the front, which is 0.1. Both of these have a sine function. Both of these have the same phase shift, right? Pi over 4 and pi over 4. So really the only thing that I need to differentiate is just this omega, because A sine omega t. Well, omega here is 6, and then omega in this statement is 4. So how do I know what the omega is? Well, that's easy. Just use the information given. Right. We know that V max, we know that KE max is 1/2 mV max square, and then once again V max is simply A omega. Sorry, my animation was out of order there. However, I'm just gonna go ahead and plug in V max again for a true statement. V max is just the amplitude times omega, and then here it's 1/2 m. When you substitute in V max, make sure you square both the A, the amplitude, and the omega. So that's where I highlighted the stuff from. It's A square, omega square. So essentially, you're given KE max. KE max is A times 10 to the negative 3. That was given in the statement. M is 0.1, A is 0.1, but don't forget to square that. And then omega square here is the only term we don't know. So I'm just going to clean it up a little bit. I'm just going to divide both sides by 0.1 and then 0.1 square. And at the same time, I'm going to multiply both sides by 2. So this 2 on the bottom right, I'm just going to move it up. That's where this is. Okay, and then the 0.1 and then the 0.1 square, I just divided that to get omega square. So if you clean this up in your calculator, on the left side, you get 16. But then this is omega square. You still got to square root both sides. So the square root of omega squared is just omega. The square root of 16 is 4. So the only answer choice that matches the omega here would be choice C. And let's go ahead and box that. All right, and that is that for this particular video. I hope that helps. Stay nerdy, don't be wired.